Section 4.6 is on isosceles and equilateral triangles. Recall from the first section in this chapter that an isosceles triangle is a triangle with at least two congruent sides. So here's a triangle, triangle ABC, and if AC is congruent to BC, then it is an isosceles triangle by the definition of isosceles triangle. We call those segments, AC and BC, the legs. Those are the two congruent sides. And AB is the third side that is not congruent to either of the other two, and that's called the base. Angle A and angle B are referred to as the base angles, and angle C is the vertex angle. The vertex angle is the one that's formed by the two congruent sides. So here's the isosceles triangle theorem. It says that if two legs of a triangle are congruent, then the angles opposite those sides are congruent. So let's go back and take a look at our picture here. Since AC is congruent to BC, then what the isosceles triangle theorem says is that angle A is going to be congruent to angle B, because angle A is directly opposite side BC, and angle B is directly opposite side AC. If two sides are congruent, then the angles that are opposite those sides are congruent to each other. The converse of the isosceles triangle theorem says the opposite. If two angles of a triangle are congruent, then the sides opposite those angles are congruent. So if we're given that angle A is congruent to angle B, then I know that the side opposite angle A, which is BC, and the side opposite angle B, which is AC, that those two sides are congruent to each other. If the two angles are congruent, the two sides opposite those angles are congruent. So let's take a look at a couple examples here. So if segment AB is congruent to segment CB, so that would be the one on the left here and the one on the right, then name two congruent angles. Well, if AB is congruent to BC, then this is an isosceles triangle, and the base angle, just ignore this little triangle inside for right now, the base angle, angle BAC, is going to be congruent to the other base angle, angle BCA. Now looking at the smaller triangle, if angle DAC, so that's this smaller angle down here on the left, is congruent to angle DCA, that's this smaller angle down here on the right, then name two congruent segments. Well, if DAC is congruent to DCA, then segment AD, segment AD is going to be congruent to segment CD by the converse of the isosceles triangle theorem. If the two angles are congruent, the sides opposite are going to be congruent. Okay, here's another example that has a lot of different triangles going on here. So if angle ABF is congruent to angle AFB, name two congruent segments. So angle ABF, okay, so that would be this big angle B right here, and angle AFB, that would be this angle BF right here, okay, then two congruent segments. Well, if big angle B and this angle F are congruent, then the sides opposite those would be congruent. So AB would be congruent to AF. I know it's a little hard to see with all the lines going on there, but you kind of need to ignore some of those. So if angle DAE is congruent to angle DEA, name two congruent segments. So if DAE, so that's angle, little angle A up here at the top, is congruent to DEA, that would be this angle E right here. Those two angles are congruent to each other in this small triangle, then the sides opposite are going to be congruent. So that would be AD is congruent to DE. And our last example here, if segment FA is congruent to HA, name two congruent angles. So FA, this long segment here, is congruent to HA, Okay, that would make that an isosceles triangle. So then the angles opposite those sides would be congruent. That would be this angle F down here and this angle H down here, but I do need to use 3 letters for each of those. That would be angle AFH, and that would be congruent to angle AHF. If you're doing a problem like this in the classwork, it might be easiest to draw this plenty big and use different colors to mark the different things that are congruent to each other. Now, following from the isosceles triangle theorem and its converse, there's a couple corollaries or little things that kind of logically follow regarding equilateral triangles. So a triangle is equilateral. Remember, that means all 3 sides equal, if and only if it is equiangular. Okay? So if all 3 sides are equal, then all 3 angles have to be equal. And conversely, if all 3 angles are equal, then all 3 sides have to be equal. And then each angle of an equilateral triangle measures 60. So if all 3 of the angles are the same measure, and those 3 angles have to add up to 180, then each angle of an equilateral triangle is 60 degrees. Let's take a look at another couple examples here. So in this one we have a triangle ABC, with an angle at the top of 120, and angles A and B are congruent to each other, and we need to find the measure of angle A. So if I'm going to start this by saying, let x equal the measure of angle A, but then I also know that angle A and angle B are congruent. So that's also going to be equal to the measure of angle B. And I know that all of the angles in a triangle have to add up to 180. So if angle A is x, angle B is also x, angle C is 120, and that has to add up to 180. Then I have 2x equals 60, and x equals 30. So the measure of angle A is equal to 30. Here's another triangle, and it says find x and y. Well, let's see. The first thing I notice is that I have 2 sides that are congruent to each other, and fortunately both of them are labeled with an algebraic expression with just a y in them. So I could start by saying AC is equal to AB. This side is equal to this side, and then let's just plug in our algebraic expressions for those. 6y plus 3 is equal to 8y minus 5. And solving for y is going to be equal to 4. Now, if AC is equal to AB, then that means that the angles opposite those are equal to each other. So angle C is going to be congruent to angle B. So I know that angle B is 4x minus 8. So too is angle C. And I know that angle A, angle B, and angle C have to add up to 180. So angle A is 4x minus 8. Angle B is also 4x minus 8. And angle C is also 4x minus 8. And that has to add up to 180. Actually, I have an easier way to do this. If all 3 of these angles are the same, then that means that this is an equilateral triangle, and each one of those angles has to equal 60. I think the math is a little bit easier for that. So adding 8 to both sides, 4x equals 68, or x equals 17. And here's a proof. It's given that, that DE is parallel to BC. I'm going to go ahead and mark that. And that angle 1 is congruent to angle 2. And I have to prove that AB, the long side on the left, is congruent to AC, the long side on the right. Okay, I'm actually going to split up my given for this one. I'm going to start with DE, oops, let me try that again. DE is parallel to BC, and that's given. So if those two horizontal segments are parallel to each other, I'm seeing parallel lines cut by a transversal. Actually, I have two different transversals, both AB and AC. So I can say that angle 1 is congruent to angle 3, because those are corresponding angles. And angle 2 is congruent to angle 4, because those are also corresponding angles. So if lines are parallel, corresponding angles are congruent to each other. Okay. Then it told me, I'm going to use this next part of my given, that angle 1 is congruent to angle 2. That's given. And it looks like I have a whole bunch of congruent angles here. But what I need to say, I think what I'm going to need to say is that angle 3 is congruent to angle 4. And I can't just say because I'm looking at the picture and everything's marked in pink that angle 3 is congruent to angle 4. I think I'm going to have to do a couple substitutions here. So let's see. If 1 is congruent to 2 and all of these guys are congruent here, I can say that 2 is congruent to 3, because what I'll do is for this first statement, 1 is congruent to 3, I'm going to substitute in 2 for 1, because 2 and 1 are the same. I can say that angle 2 is congruent to angle 3 by substitution. And now I'll use that along with 2 is congruent to 4. If 2 is congruent to 3 and 2 is also congruent to 4, then I can say 3 is congruent to 4. Again by substitution. Now I know you can see that very clearly just by looking at the picture and by what we've marked, but I need to actually logically come up with the statement angle 3 is congruent to angle 4 using valid reasons. So if angle 3 is congruent to angle 4, then I can say that the sides opposite those angles, or AB and AC, are congruent to each other by the converse of the Isosceles triangle theorem. Oops. Okay, and let's take a look at one more proof here. So given angle 1 is congruent to angle 2, 1 is congruent to angle 2, I have to prove that AB is congruent to CB. So in other words, this side here is congruent to this side here. Thinking backwards a little bit, I think I would like to show that angle 1 is congruent to angle 3, because if those two angles are congruent to each other, then the sides opposite those are going to be congruent to each other. So let's start with our given. 1 is congruent to 2. And then looking at the picture, I see that angle 2 and angle 3 are vertical angles. So I can actually say angle 2 is congruent to angle 3 because vertical angles are congruent. And now if 1 is congruent to 2 and 2 is congruent to 3, then I can say angle 1 is congruent to angle 3 by the transitive property. Or you could say substitution if you'd like. And now that I have angles 1 and 3 congruent to each other, I can say that AB is congruent to CB, because those are the sides that are opposite two congruent angles, and that would be the converse of the Isosceles triangle theorem.